Hi, my name is Andrew Norton. I'm an associate software developer at Capital One right now. However, this presentation is entirely based off of work that I did while at the University of Virginia studying under Professor Jane Chi. So my presentation is on Adversarial Playground. This is a toolkit that we built to help researchers and practitioners investigate the impact of adversarial learning or adversarial machine learning. So very briefly, I'm going to talk a bit about the background of what is adversarial machine learning and how does this relate to what we've heard about with deep neural nets and that sort of thing. Then talk about our approach to solving the problem with our user interface that we've developed, features that we've included, and then a small improvement that we've made on a state-of-the-art algorithm to make it more conducive towards visualization purposes. And then I'll close with a short demonstration and future work. So as a brief introduction, this is a toolkit. The goal is to help practitioners, educators, and researchers understand how some machine learning model that they have built might withstand attacks, or how new attacks that people have developed might work against commonly known models. And the result is an easy-to-use web app that we've made completely open source on GitHub. And so as a brief background, pardon. So the field of adversarial machine learning, we study classifiers, which take as input some, in this case what we're looking at as an image. It can be other data types, but for now we'll focus on images. This classifier takes in an image and produces some type of class. For instance, it looks at this handwritten 2, does some math, and comes up with this is an instance of the handwritten 2. However, adversarial machine learning looks at how can we slightly modify the input by maybe adding a few pixels or changing it so that it misclassifies the output. However, for a human, it still looks somewhat like a 2. This way, we're kind of like looking at the very boundary cases of what your classifier is performing. There's two different types of attacks. There's targeted and untargeted attacks. Targeted, it's very specific. I have a 2 and I want it to look like an 8. Untargeted is I just have a 2. I don't care what it ends up being classified as, but I want it to not be classified as a 2. Of course, we don't want to just completely change the image in a way that everyone knows this has been modified. And so we minimize the alterations we make to an image based on some type of norm. In general, you can use a lot of different norms. Two popular ones are the L0 and L infinity norms. These are what we incorporated into our visualization platform. This is minimizing respectively the number of changed features and then minimizing the largest change to a single feature. I'm using feature and pixel here interchangeably. Briefly, deep neural networks and MNIST. Deep neural networks and convolutional neural networks are effective devices for classifying images and other type of data, but we're looking at images here. They're based on layers of compositions of nonlinear functions, but they haven't really been designed with adversaries in mind in the security environment. So another piece of background, MNIST is a standard handwritten digits data set that's been used as a benchmark across a large amount of machine learning. It has 60,000 training images, 10,000 testing images, and that's where I got the image of the 2 that I showed just recently. And finally, as a little bit of an inspiration for our work, Google had released a TensorFlow playground where, in conjunction with their TensorFlow toolkit, this is a JavaScript-based, interactive, web-based demonstration of how deep neural networks can be designed. This was lightweight, utilized JavaScript entirely. We took this as an inspiration and wanted to make something similar, but for adversarial machine learning. And so moving on to a brief look at our user interface and our features. And so Adversarial Playground features a pre-trained convolutional neural network classifier for the MNIST data set. And it allows users to select from any one of 3 adversarial algorithms. The first 2, fast gradient sign and Jacobian saliency map approach, have been published and studied in literature. And then finally, we had noticed that the Jacobian saliency map approach was a bit slow in visualization. This isn't so great. And so we made an improvement to optimize the speed, approximating the result of a Jacobian saliency map. the user can select different types of input images and hyperparameters for the attack algorithms, and then display the input image, adversarial output image, and then the classification likelihoods for each class. We chose to do a web-based visualization. This allows the web app to run on a server or locally on your own machine, but if you run it on a server, then anyone in your organization could access it, and even if they don't really have a super high-powered computer, this might be helpful if you're trying to explain adversarial machine learning to someone who isn't a researcher in the field and doesn't have the hardware on their own computer. A client-side only functionality would be nice, but again, due to the math that's involved in creating adversarial samples, we needed to offload some of that to a GPU, which is a little bit difficult in client-side only code. And so what we have is a system layout kind of like this, where on the client side, the user selects hyperparameter as the input for the visualization. They send that off to the server side where we have Python and TensorFlow running. In a modular framework, we have the adversarial algorithm and the convolutional neural network, and you can replace either one of these fairly easily. So that if you wanted to look at a different convolutional neural network or a different adversarial algorithm, you could switch those out. You get the response and send it back to the client where it's displayed using the Plotly libraries, and then the user can see from there. Briefly, going back to the improvement that we made, talking about the Jacobian saliency map approach. This was developed by Papernaut in 2015. At a very high level, you can think of this as it's selecting pixels from a saliency map of the forward derivative of the classifier. You can think of the saliency map as kind of like a importance metric that's on every single pixel. Something with a high value that pixel has a very high impact on the classification of the image. And so if you change that, you might actually impact the classification considerably. And so they were looking at all pairs of pixels and then selecting the pair with the highest combined saliency map score. And they keep repeating this, selecting 2 pixels and modifying them until this image is either misclassified, we succeeded and created an adversarial example, or the image was too different. We modified too many pairs of pixels and it no longer is considered to be enough like the original image. The problem is that this is kind of slow. The all pair search is quadratic time. You can't really get around that. Yeah. And so what we did was we just decided to approximate the Jacobian saliency map approach using a greedy heuristic. Instead of considering all pairs, we forced one of the pixels in that pair to be from the top k pixels when weighted by the saliency map. And it turns out that you can make this k fairly small and still get the same results, just empirically. We actually tested this by looking at the performance of our fast Jacobian saliency map approach, where we looked at the evasion rate. And so the evasion rate is a measure of how successful the attack was. Because we're limiting how different we can make the images, right? If we allow so much distortion in the image, we want to see so many images actually be successfully turned into adversarial samples. And so when we look at this, we can see kind of this a converging effect towards the Jacobian saliency map performance. As far as timing goes, our fast Jacobian saliency map approach ran anywhere between about 60% to 50% of the Jacobian saliency map time, which was a substantial speed up for the visualization. And so now I'll give a brief demonstration of our tool and how it works. Okay, so we have, it's a web app, so we actually have a little bit of information on how all of adversarial machine learning works, kind of a brief overview on the home page. But what we can do is we can select from the top any one of the 3 different attack algorithms. We can do this fast gradient sign method. And let's just make sure that this is running. Okay, so what we can see is that we have the original samples already selected. We can choose different samples. and adjust to this attacking power of the algorithm. We can make it a little bit bigger for being noticeable. We say generate, and it produces an output image in real time, not just like restoring some cached value. And then you can see if you scroll down, likelihoods of each classification. And so here for the original input, we can see that the class 3 is very high likelihood. But then for the distorted adversarial example, we can see that the class 8 was the highest likelihood value. And we can see it summarized here that it actually, the adversarial example was classified as an 8. This is an example of one of the untargeted attacks, right? We don't really have a target as to what we're aiming for. We just want it to not be classified as a 3. If we come to the fast Jacobian saliency map that we talked about, here, in addition to selecting some type of input, we can also select a target class. And so I may want to send this 4 and make it appear to be an 8. I can say generate, and then in a little bit. This again will take a little bit longer, but it runs, and with modifying a few pixels, it still looks somewhat like a 4 to a human. It classifies as an 8. And we can see here how originally it may have been a 4, but then now the 8 classification just barely edges out the 4 classification. And so this is kind of the way that the system works. So going back to this, we have some future work to be pursued. Yeah, so some things that we could incorporate are other image input types. For instance, using the CFAR and ImageNet data sets, these are to like color images of different types, like cars and cats, not just 2s and 3s. A bit more interesting to the average user. And also, possibly using non-image input. Something that's been recently studied a lot would be malware classifiers in PDFs, and so finding some way of visualizing that and displaying that could be really useful. Another thing would be to show more adversarial algorithms. For instance, there's L2 norm approaches that have been investigated, and actually new approaches for the L0 and L infinity norms. One of the reviewers to my paper had pointed out that while my paper was under review, someone had come up with a hardware accelerated JavaScript library, and so I could possibly incorporate that in the future as well. A colleague of mine, Wei Lin, also might take this work and incorporate it in a package that he's developed, which is like a one-stop toolkit for adversarial machine learning, not focused on visualization, but using this to kind of jumpstart a visualization part. Again, all the code and data for my experiments is available on our GitHub page. If you just Google Adversarial Playground, it comes up, but that's also the direct link. Thank you.